This lesson is on coordinate proofs with quadrilaterals. I hope you've done this with triangles, although if you haven't, hopefully you can catch up. Some things to keep in mind. So a coordinate proof is essentially when you're asked to prove something about a general shape. Prove this about squares. Prove this about rectangles, and so on and so forth. When we're asked to do that, what we do is we choose a general rectangle or a general square, whatever the shape is, set it in the coordinate plane, provide it with its own vertices, and then construct the proof based on that general shape. What we need to do, we need to always make sure that one of the corners, one of the vertices of our quadrilateral is the origin. It's easy to work with 0 and 0. We would like one, if not both of the, if not two of the sides of the quadrilateral to be along the axes. Always along the x-axis, sometimes along the y-axis. We also want to make sure that we have as much of the shape in the first quadrant as possible. Typically, we can do that with all of the shape. And then finally, when we pick coordinates, we need to be careful. We're going to choose the variables as coordinates, but sometimes, for example, if you're using the midpoint formula, you know you're going to be dividing by 2, and so it's helpful to use, for example, maybe 2a instead of a. That way, when we divide, we'll have a instead of 1/2 a. Okay, when we create coordinate proofs, it's not like a 2-column proof where we're referring to postulates and theorems. We really just use 3 tools, which we're very familiar with. We've used them a lot in this chapter: the slope formula, the distance formula, and finally, you guessed it, the midpoint formula. For quick reference, I'll provide those now. The slope formula is, of course, the change in y divided by the change in x. If you don't like my delta, then you can always write it like this: y2 minus y1 over x2 minus x1. The distance formula, the square root of x squared, the change in x squared plus the change in y squared, and then you take the square root. If you don't like the delta, again, replace this with that. Replace this delta y with that. And then finally, the midpoint formula, I'm not going to write it down. You simply average the x's, you average the y's. Okay, so if they ask me to write a proof about a square, I need to place it somewhere in the coordinate plane. The first point, of course, is to make sure it's on the origin. So I'm going to do that. I'm also going to try to make sure it's along the x-axis. We get a bonus here with this shape because it's got a right angle. So if it's along the x-axis, it's also along the y-axis. Okay, and now we need to give it coordinates. Again, we're not proving this for one square, we're going to be proving for all squares, so we choose general coordinates. That is to say, instead of picking actual numbers, we pick variables. Now, because we set this in the origin, regardless of the width of the square, this point is 0, 0. I'm going to now name this point. I can look at it and tell that the y-coordinate is 0 because it's on the x-axis. I have to decide how wide I want the square to be, and again, I'm going to use a variable so it can stand in for any square ever. I'm going to call it a. So the width of my square is a. Because this is a square, that means it is also a tall, and so when I label this point, again, obviously the x-coordinate is 0 because it's on the y-axis, it's a tall, just like it's a wide. And then finally, how do I get here? Well, it's a wide and a tall, so that's a to the right and a up. Just another reminder, if I were going to use the midpoint formula at some point, then I would probably want to double all of these variables. A rectangle is very similar to a square. I'm going to try to get through this quickly. We want to be on the origin, on the x-axis. Bonus, we're on the y-axis. Label our points. Always have 0, 0 there. That's nice. I'm going to label this guy A0. A is a little bit longer this time than last time, apparently. And, of course, that's still 0. X-coordinate here is obviously 0. How tall I go up? Well, it's not a square, so that this side's probably not the same length as that one. I'm going to call it B. And then finally, how do I get to this point up here? Well, it appears that I go A to the right, and I go up B, so there's this point A, B. A couple more of these, we'll be ready for proofs. Okay, I'm going to assume this is a parallelogram. I want to turn it, not that much. I want to turn it so that I can set that on the origin. Okay, it's along the x-axis. Only one axis this time. Again, always the point 0, 0. Frequently we'll have here the point A0. I don't know how wide it is. And okay, we're going to do parallelogram. So I've got to go over a little bit. I don't know how far. I'll call it B. And then I go up some more. I don't know how far. I'm going to call it C. And my guess is you're tempted to call this point DE, but it's not quite that. So to get to this way over here, I have to go A, that's the first part, and then I've got to go a little bit more. I've got to do this right here, which you're like, I don't know, but if I look carefully, because this is a parallelogram, I can prove that this distance and this distance are the same. That distance is B. A plus B, comma, how high do I go up? Well, it's the same height as this over here, so the height is C. Okay. A trapezoid, I'm going to assume it's an isosceles trapezoid. There's not a lot to prove about other trapezoids. Okay. Sliding this over, make sure I'm in the origin. I want to be along the x-axis. Check, check. Alright, I'm in the first quadrant. Let's label these points. Always 0, 0. We'll call this A0, don't know how far it is over. And now I've got to figure out these other two guys. Well, this point here, I have no idea how far to go over. I'm going to call it B. I have no idea how high to go up. I'm going to call it C. Again, you might be tempted to say, well, it's just, I don't know. I'm going to call it DE. Well, to get here, if I think about it, I can go past it and go all the way to A. And the question is, well, how far do I need to go back? I need to go that far back? Well, I hope you'll trust me that because this is a congruent, an isosceles trapezoid, this leg and this leg are the same. Therefore, this and this are the same. So I go A forward, but I have to backtrack a tad. I have to backtrack B, and then how high is it? Well, it's the same as that, C. All right. You're going to have homework problems like this. Name the missing coordinates. This is very similar to the one we just did. It's actually exactly the same. Again, how far do I go over? I don't know. Well, if I went to get to this point, I have to go A to the right, and then I have to go back B to the left. So this distance right here is B. This distance is B. This height over here is C. Well, this height's the same thing. They're across from each other. There's the missing. Okay, our final exercise, a proof to end the lesson. How does this coordinate proof work? Well, it says prove that the diagonals of an isosceles trapezoid are congruent. So I determined I need to have an isosceles trapezoid on the coordinate plane. I've put it here. We've worked with this a couple times already. So we're going to make the proof using this. We have to prove that the diagonals are congruent. So let's figure out exactly what our diagonals are. The first one is going to go from D to the opposite corner, so DB. And the other one is going to go from C to A. I need to prove that these two diagonals are congruent. Well, they certainly look congruent, but I have to prove it. The way that I prove things are the same length in the coordinate plane is to use the distance formula. The first distance I need to find is AC. It is the square root of the change in x squared plus the change in y squared. Well, how far apart are 0 and a minus b? I take the larger one and subtract the smaller one. A minus b minus 0 is simply a minus b. Square that. And now I have to add the change in y squared. The large y minus the small y. C minus 0 is c. I square that, I'm done. Now, this is very ugly, and I can't do anything with it. I have to leave it alone. Hopefully the other one is equally ugly. So we'll look at segment BD. Same formula. What is the change in x? I'm going to take the large x, subtract the small x. That's a minus b. And then I have to square that change. Okay. The change in y. The big Y minus the little y. C minus 0 is C. So both of these are very ugly, but as you can see, they're equal to each other. AC equals BD. That means the segments are congruent, and that's exactly what we were asked to prove.